All right, so today's lecture is on implementing a generic queue. So I think you've all seen queues before, so let me just quickly remind you of what a queue data structure is. So a queue is just a line of items, right? So it's an ordered sequence of items, and there's a front and a back of the line. Right? And so in a queue, it's similar to a stack. In a stack, everything happens at the top of the queue. At the top of the stack. In a queue, everything happens at the front and the back. Right? So it happens at both ends of the data structure. So there's only two classic operations. You can enqueue, so add to the back of the queue, and you can dequeue, remove from the front of the queue. And of course, it's an error to try to dequeue an empty queue. Obviously, you might want to add extra operations to make a more functional data structure. Right? So knowing the number of items in the queue is useful. If you know the number of items, you can easily check if the queue is empty. Some queues let you look at the first element without removing it. Some queues let you look at the back element or remove the back element. And some queues, you might have a contains method that finds or searches a queue for a specified item. Right? In Java, you'd probably do toString equals hash code and perhaps some other methods. Right? OK, so what does this look like as a picture? So in an empty queue, there is no front or back of the queue. Right? As soon as you enqueue an item, right, that just joins the queue. Well, you end up with a queue of one item, so it joins the queue at the back. Right? So I'm going to use F and B to point to the current front and back of the queue. Right? If you enqueue a second item, B, so B appears at the back of the queue, and then your whatever you're using to record where is the back of the queue, that now updates. Right? When you enqueue another item, you add the item to the back of the queue, and you update where is the back of the queue, right? And so on, and so on. OK, so when you dequeue a queue, now dequeuing a queue, I forget if I've updated these to make this picture less deceptive. OK, so I'm going to do it this way. So when you let me back up. So when you dequeue a queue, the first element in the queue is going to be removed. So we remove the A. Right? And now all of the other elements shift forward one position in the queue. Right? Now you should think about this. So if you're implementing this as an array, and you want to shift all the elements forward in the queue, right? That's going to take O(n) time, right? Where n is the number of elements in the queue, because you have to move n minus 1 elements. So we're not going to do it this way. To dequeue another item, right? So the B is going to disappear or come out of the queue. And then the rest of the elements move forward, right? And so on, and so on, and so on. Come on, let's go, until you have the empty queue again. OK, so a queue is a first in, first out data structure, right? The first element that goes into the queue is the first element that comes back out, unless you're implementing a priority queue, but we're not going to do that. Where do you use these things? So it turns out these are used very widely in computer science. So if you're on a website of some kind, your request to the website almost certainly goes into a queue of some kind, right? Because it's probably the case that many people are trying to use well, on a busy website, many people are trying to use the website at the same time. So every time they hit the website for something, clicking on a link or something, that request goes into a queue. The web server then deals with the requests in order. Operating systems make very wide use of queues. Because they have to manage resources, right? Finite resources. Right? So if you have a printer or your disks or your CPU, right? Those are all finite resources on a computing system. They're all typically managed with a queue. Similarly with network devices. Probably the most famous, I would argue the most widely known algorithm that uses a queue is Dijkstra's algorithm. Right there. So Dijkstra's algorithm is an algorithm that searches for the shortest path between two nodes on a graph or two nodes on a tree. So if you're trying to go from A to B, and every time you move from a node to a node, you have to pay a price. So the price is written as a number on the link. And then you want to know what is the smallest cost or the shortest distance between two nodes. Dijkstra's algorithm is probably the most well-known algorithm for solving this particular problem. Right? And notice right here, it uses a queue to solve this problem. Oh, there's actually a whole there's a whole branch of mathematics and computing science devoted to this sort of thing. So if you're in electrical engineering, maybe math, you might run into queuing theory. Okay, so I want to actually implement a queue. And so we're going to do the same thing we did with the stack, except now we know about interfaces and generic classes, so we might as well just start there right to begin with. So the first thing we're going to do, we're going to create a queue interface. Right? So it's generic, so the queue can hold any type. For our methods, there'll be a size method, there'll be isEmpty. Notice that isEmpty is a default method, and we can implement it in the interface because all we need is the size method, which is also defined in the interface. Right? So we can actually implement isEmpty. When you implement a default method in the interface, people who implement the interface when they go to make their own queue class, if they want to, they can override this method if they have some reason to do so. They probably don't, but if they wanted to, you can override a default method. There's enqueue, so enqueue takes an element, adds it to the queue. Right? dqueue removes the first element in the queue, returning the element. Right? We're going to add two more methods, front and back, that let the user get the front and back element of the queue without removing them. Okay, so if you use a list, then it's almost the exact implementation as stack, right? Except where in a stack we removed the element from the back of the list. Now you're going to remove the element at the front of the list. You don't want to do it this way. Right? So here's list queue. Right? It's going to implement our queue interface. Internally, it just has a list of some kind. If you happen to choose array list, this is going to be a bad choice, but I'll explain why in just a second. Right. So our constructor simply makes a new empty array list and sets queue to refer to the list. Right. The size of the list is easy. Right. You just ask, sorry, the size of the queue is easy. You just ask the list for the size of the list. Enqueue is dead easy. You just add the element to the end of the list. Right. And dqueue, where's dqueue? dqueue is also easy. Right? You just remove the first element of the list. Right? Of course, you have to check if the list is empty because you can't dqueue an empty queue. So I have a little method here, a little private method here that actually tests if the queue is empty and throws an exception if it is. Right? The reason you don't want to do it this way with an array list is because when you're removing the first element of an array list is in big O-N. Right? To remove the first element of an array list, you remove the first element, but then you have to shuffle all of the following elements forward one position. And that takes big O of n. If you have a linked list, it's big O1. But you have another problem in a linked list. In a linked list, depending on how you implement it, you may not have a reference to the last node of the list, in which case adding an element at the back of the list becomes big O of n. Okay, so front and back, so now you can see the reason why I have a throw if empty method is because I have to do this everywhere. Right? If you want the first element, you can only get the first element if the queue is not empty. Right? So rather than repeating the validation, I use a method instead. Right? It's easy to get the first element of the queue. And similarly with the back, it's easy to get the back element of the queue, right? Because we have a list. And toString is easy as well. Because you can just ask the list for its toString implementation. Right? Similarly, equals and hash code, you can just reuse the equals and hash code methods from list. Right? And everything will work just fine. So easy to do. Yes?
Well, what's stopping you from like dequeuing something in the middle of the...
It's not, we're using composition. It's not, this isn't inheritance.
Okay.
Right? So there's no way for someone who's using the queue class, the linked list queue class to dequeue from the middle of the queue.
Like because it's composition, I can't do q dot remove like 3.
It's private, right? So inside the class you can, but anybody who's using the class can't see inside the class, right? Because all the implementation details are private.
Okay.
Yeah. But internally, yes, you could remove something from the middle of the queue.
Okay.
Yeah. Okay, so we want to try to get away from this big O-N dequeuing problem, right, that you run into if you use an array list. So you can if you use a plain old array, but now implementing the queue becomes considerably harder than implementing a stack. Right? So the fact that remove and add occur at the different ends of the queue makes implementing the array-based queue somewhat tricky. Right? So in a stack, all we had to do is keep track of where was the top of the stack. In a queue, we're going to have to keep track of where is the front and the back. Right? So we have the array to hold the elements. Right? We have the size, so the number of elements that are currently in the queue. Right? Front is going to be the array index of the element currently at the front of the queue. And back is going to be the array index of the element currently at the back of the queue. Right? Unless the queue is empty, in which case front and back are going to be, well, they're going to look like this for the brand new empty queue. It's going to look like this, right? But in a general empty queue, it could look different. So we'll see what I mean by that in just a moment. So I think, let me just quickly check through these slides. Front, yeah, okay. So front is going to be is going to refer to the element that's currently at the front of the queue, unless the queue is empty. Right. So here's my array. Right. I can hold 16 elements. Front points at 0, and back is pointing at, I guess, -1 in this case. Right. So back is less than front. All right. So to enqueue an element, that's going to be similar to pushing an element onto a stack. Right. So if our size is equal to the length of the array, then our array is full. So I have to make a new array. And then I have to do something with the elements in the current array. But it's not as simple as just copying the existing elements into the new array. There's something else we have to take care of. So remember, when we enqueue, we're adding to the back. So we're going to move back one position to the right to indicate that we've got a new element in the queue. And then we're going to set the element at array back to the enqueued element. Right? This is exactly the same as with the stack, except back, top is now back. Right? It's the exact same thing. Right? So after one enqueue operation, right, we've added the A. So back goes to the right by one position. So it now points at the 0. Right? The A is in the queue. Did I miss a step here? I missed a step. The size goes up by 1. Step 4. Size goes up by 1. Right? And the size is now 1. Right? Notice that nothing happens to the front, because when you enqueue, you never touch the front element of the queue. Right? All enqueues happen at the back. So second enqueue. Right? So we add the B, so back moves to the right one position. Size goes up by 1. Nothing happens to the front. Right? Enqueue again. And again, 2 more times. Right? So now I've got 5 elements in the queue. So what about dequeue? I'm missing a step in here too. Right? So to dequeue the element, right, I need to get the element at the front, but I know where that is because I've got front. Right? So I need to remember that the A is here. Right? Obviously, I'm going to move front one position to the right to simulate moving all of the elements forward one position to the left. Right? I don't want to shuffle the B forward, the C forward, the D forward, and the E forward. Right? Instead, I just want to move front one position to the right, and that saves me the big ON cost of removing an element from the queue. Right? I am going to null out the element in the array this time. So unlike the stack, where I didn't do it, I am going to remove it from the queue. And then I'm going to return the element that was in the queue, and I have to decrease the size of the queue by 1. Right? So back here. Right? So if I'm going to dequeue the A, right? So the A goes out. I'm going to return the A. I'm going to set that its old position in the array to null, and I'm going to move front one position to the right. Right? Dequeue the B. So remember what the B is. Right? Set the array element to null and move front one position to the right, and so on. Right? When front and back both point at the same element, it looks like there's only one element in the queue. Right? To dequeue the queue, the E is going to come out. Right? Front's going to move one position to the right. Right? And again, right? So just like when we had a brand new queue, back is now in front of front. Right? So back is less than front now. And you might think that this is a reliable way to test if the queue is empty, but it turns out it's not. Right? So back can be less than front, and the queue is not necessarily empty. Okay, so in queue again, right? So add the element to the, move back one position to the right, add the element to the queue, right? Size goes up by 1. Right? And now if I keep on enqueuing, right, until I hit the end of the array, right, I now have to deal with how do I move back to the right. Right? Because the queue is not full, right? There's space at the front of the array. So the queue is not full yet, but back is now at the end of the array. Right? And so when you enqueue again, you have to wrap back to the front of the array. Right? So back wraps around to the front of the array, right? And now you see that back can be less than front in a non-empty array. And if you keep on enqueuing, right, now the array is full. Right? Back is again one position to the left of front, and instead of the queue being empty, the queue is now full. Right? So you can't use the condition of back being one less than front to determine if the queue is empty or not. Okay, so there's my full queue. Right? I'm going to start dequeuing now. So when I dequeue, the front element's going to come out. Right? And I can do that several times. Right? And now the same thing happens to front. Right? If I dequeue again, I have to wrap front around to the front of the queue again, to the front of the array. Right? So front also wraps around. Right? And so if you imagine the array as just being a circular array, right? Then that's one way to visualize a queue. Right? So this is a queue of finite capacity. In this case, it can only hold 16 elements. Right? When you view it as a circular array, front and back always move clockwise around the circle. Right? So if I, do I have a picture? No. So if I dequeue front, right, the queue comes out, and then front moves clockwise one position. Right? If I enqueue to the back of the queue, right, a new element appears here, and back moves one position clockwise. Right? And so queues are often implemented as circular arrays, which is what we're going to try to do here. Right. Okay, so how do you actually implement this thing? So we need an array to hold our elements. So just like in the stack, or the generic stack, we're going to use an array of object to hold the elements. I need to know where is the front element in the array, and I need to know where is the back element in the array. Right? And I also need to know how many elements are currently in the queue. Right? So I have the size here as well. Okay, the no argument constructor makes an empty queue. Right? So what does it need to do? Well, it needs to initialize all 4 of our fields. Right? So our array becomes a new array of object of size, whatever default capacity is. What is it, 16 here? Right? You can pick whatever number you want here, right? 1, 2, 4, whatever you like here. Front is 0, back is -1, and size is 0. If you want to copy another queue, right, then that's pretty easy as well. Right? I need to copy the front index of the other queue. I need to copy the back index of the other queue. I need to copy the size of the other queue. I also need to copy the array, and that's easiest using arrays copy of. If you want to, you can make a new array and then write a loop, but arrays copy of is much easier. Right? It does everything for you. So it makes a new array of that length and returns a reference to that. Oh, it copies the elements from that array and returns a reference to the new array. Front. So I really should have put in that test method again, which I didn't do. Right? Okay, so if the queue is empty, throw an exception because there is no front element. Right? It's easy to return the front element because I have the index of the front element. Right? All you have to do is remember you need to cast it to the generic type E because our array is of type object. Right? When you do this, the compiler is going to, Eclipse will show this in orange. So it's going to tell you there's a possible problem here. Right? So Eclipse is saying that you're trying to cast the element type object to E, right? And it's trying to say that might be an unsafe cast because there's no way for the compiler to know, right, that the type of objects in the array are in fact of the generic type, right? You know, as the implementer, because when we implement NQ, we're always going to be adding an element of type E. Right, back is the same. We have a reference to the back element. Sorry, we have the index of the back element, so we can easily access the back element of the array. Okay, DQ, you just implement the algorithm that was on the slide. Right, so remember, what is the element at the front of the queue? Right, because that's the element I have to return back to the caller. I'm going to return that element back at the end of the method. I want to set the current element in the queue to null, the current front element of the queue to null. Right? So that erases the element from that erases the reference from the array. Right? Now I need to advance front one position to the right. Right? So I want to add 1 to front. Right? But I also have to wrap front around to the front of the array. Right? If front happens to be at the end of the array right now. Right? And the easiest way to do this is just to use the remainder operator. Right? So if the size of my array is 16, right, and this front is 15, so it's pointing at the last element of the array, right? Then when I add 1, that becomes 16, right? 16 divided by the length of the array, which is 16, is 1 with a remainder of 0. Right? So the remainder operator is super useful here. You can just compute the remainder every time, and that correctly wraps the index to the front when it needs to. Right. Don't forget to decrease the size of the array by the size of the queue by 1, and then return the element. Okay, so resizing the array becomes slightly complicated. Right. Because the order of the elements is not necessarily from the beginning of the array to the end of the array. Right? So suppose you have a queue that looks like this. Right? So it's full. Front and back are somewhere in the middle of the queue of the array. Right? So they're not at the front. Right? So front's not front's not here, and back is not here. Right? So if you just use arrays copy of to copy this array into a bigger array, then what happens is you get a bigger array. Right? You copy all the elements from the old array into the new array. Right? You're going to copy back and front as well, but now you see there's a problem. Right? The back of the queue is actually over here. Oops, sorry. Right? But back is pointing to the U here. If you make back point here, you have a second problem. Right? Front is pointing at the correct front of the queue, but when it hits the P, it's not going to wrap around anymore. Right? So it's not going to find, you're going to lose the Q, R, S, T, and the U. Right? So copying the array this way doesn't work. So you have to be a little bit more careful about how you copy the array, the old array, into the new array. Right? And there's many different ways that you can do this. Right? So the easiest way to do this is to unwind the array. Right? So in other words, when I copy the queue, the old queue into the new, the old array into the new array, I'm going to start at the front. So I'm going to take the first element, the front element of the old queue, and copy that into index 0 of the new array. Right? And the second element of the queue, I'm going to copy that into index 1, like that. Right? And so on and so on and so forth. Right? So now you end up with front being at the front of the array, back is at the last element of the queue in the new array. Right? And now I can correctly add or NQ more elements into the array. Right? Everything works out just fine. That's not the only way to do it. Right? So I can do this step here. Right? And then I can copy or move these elements to the end of the array. Right? And then adjust the back so that it also points at the new back element. Right? So you could also do it that way. And that would be fine as well. Right? So let's do it the way I showed you. So ignore this part up here, because this part up here deals with what happens when you have to resize the array. Right? So if you don't have to resize the array, right, then all you do is you move back one position to the right. Right? So this back plus 1. right? You have to wrap it around if it goes past the end of the array. So compute the remainder after dividing by the length of the array, right? Then you set the element at the new back index, right? And then you increase the size of the queue by 1, right? Okay, if you have to resize the array, right? Make your new array, right? So here, now we have to do it manually, right? So we make our new array. I'm going to double the capacity of the existing array. That value can be any number, but it has to be bigger than 1, right? If you want average O1 performance. Copy the elements from the old array into the new array, right? So you have to be careful about the indexing here. So for my index I, I'm going to use that as the index in the new array. Right, so I want to copy into the new array starting at index 0, right? Going up to, but not including the size of the queue, right? So the number of elements in the queue. So temp I, that's going to be the destination element in the new array. Now, where are they coming from? Right, so they're coming from the current array, right? Starting at the front index plus I. Right? But remember, the front index can wrap around. So again, take the remainder after dividing by the length. Right? So the remainder operator turns out to be really useful in this particular problem. Once you've copied the elements into the new array, set your current array, well, set your reference to the internal array to temp. Front is now 0, and back is now this size minus 1. Right? So you have to adjust a bunch of your fields now. Right, but you now have a correctly working queue, array-based queue. Oh, okay. So when you're working with generic data structures, you can create a copy constructor for your class, right? So I can have array queue, right? Copy another array queue, which I think we have, right? We did that, right? Yes, we did, right? So there's our copy constructor, right, for array queue. So it can copy another array queue. But when you're implementing generic data structures, it's often useful to be able to copy a queue of some other type, right? So instead of copying an array queue, can I just copy a queue, right? Remember, queue is the interface type. So can I make a copy constructor that copies another queue, where that queue, you have no idea how it's implemented, right? You just know that it's a queue, right? So you don't know that you don't know if it has an array inside of it. You don't know if it has a list inside of it. You don't know if it's a linked sequence of nodes, right? So how would you implement that copy constructor, right? So that's worth thinking about, right? Similarly with equals, right? So in equals, it makes sense that you want to compare two array queues for equality, right? That's actually not as easy as you think it might be, right? Because you don't know, their internal arrays might be different, right? Because we're using a circular array, right? So you might have a queue whose front element starts at 0, right? And that might be equal to another queue, but that front element is starting somewhere else, right? So it's not just the simple matter of testing, are the arrays equal? Right? You actually have to iterate from front to back and determine whether or not the elements are in the correct order. Right? But similarly in equals, it's probably useful to determine if this queue, this array queue, is equal to another queue, right? Instead of another array queue. Right? And again, the problem that you run into is that you don't know how the other queue is implemented. Right? So you don't know if there's an array in there, you don't know if there's a list in there, you don't know if it's a linked sequence of nodes. Right? So when you implement these two things, right, the way you have to do this is you have to only use the queue interface to implement these methods. Right? And so these are worth thinking about how you might solve this problem. All right, so I'm not going to, oh, actually, I guess, does anybody have any ideas how you would do this? Anybody? So let's look at the copying one first, right? So in the copy constructor, So let's go back and look at our implementation. Okay, so if you're going to copy another queue, but you don't know how the other queue is implemented, right? What that ends up being is that you end up writing a constructor, and you have to set all your fields, right? So step one, you're going to make a new array, right? How big is the new array? How big is your array going to be? Well, it's going to be at least equal to the size of the other queue, right? Can you get the size of the other queue? The answer is yes, because queue has a size method, right? So I know how big to make the array. So that's step one. Right? Step two, what are you going to set front to? Probably makes sense to set front to the 0, right? The start of the array. What are you going to set back to? It probably makes sense to set back to the size of the other queue minus 1, right? So in other words, I'm just going to copy the elements from the other queue into the array, right? Starting at the front of the array, right? Size is just equal to the size of the other queue, right? And now you have to figure out, how am I going to copy the elements from the other queue into this queue? Right? So how do I copy the elements from other into the current array, given that I don't know how other is implemented? Yeah?
Can you just loop through the values of the other queue and then?
You don't have direct access to the values in the other queue, right? You don't know what's in the other queue, so you can't just write a loop over an array or a list or something else. But you can write a loop, right? So that's correct. You do want a loop that runs n times, right? Where n is the size of the queue that you're copying. Yeah. Yeah. So if you dequeue from the other one, what do you do with the dequeued element? Okay. And now your copied queue is now one element too small, right? You've changed the queue that you're copying, right? And so this is a common approach that many students will take, right? They'll say, oh, I just dequeue the other queue, right? And put the dequeued element into the new queue, right? The problem when you do that is your copy constructor now has a side effect, right? So the side effect is it now changes the queue that's coming in. If someone is copying another queue, they probably don't want the other queue to permanently change, right? So you have to do one more thing. So what do you do with the dequeued element? Yeah, you put it back into the queue, right? So you're right, you dequeue the element, but then you just stick it right back into the end, and you make sure that the loop runs n times. Yes?
Can we use the is type method from
The instance of?
Or is of?
Instance of, right?
Or instance of?
Yeah, so what would you use instance of to do, for example?
I guess you would find out, because like when we're copying a generic queue,
Yep.
that queue isn't actually generic. It has a type at that point, right?
Ah, that's a good question. So the fact that the E shows up here as well means that you don't actually need to know the element type of the other queue, right? Because when you dequeue the other queue, you're going to get an element of type E. When you enqueue the other queue, you're also going to get an element of type E. So I think what you're asking is if I make a queue of integer and I try to copy a queue of double, right, is that going to cause a problem? The answer is no. The compiler won't let you do that. So when you make your new array queue, you're going to write new array queue and then integer, right? Array queue integer queue equals new array queue. Equals new array queue. You're going to call the constructor and pass in the other queue, right? If that type here is different, so if that's double, the compiler will tell you you can't do it. Yeah.
So what if we create a second copy of the other queue, and
Yep.
from that second copy of that queue, dequeue those values?
Right. So that works, but what's the disadvantage to that?
It takes a lot of it's expensive. It takes a lot of time.
It's not the time. Well, it does take time. So you need time to make the copy. The problem is it takes twice the amount of memory too, right? You need memory for the auxiliary queue, the temporary queue. Yeah.
Could we use like an instance of to cast queue to array queue and then copy?
No, that doesn't work, because the conversion won't work, right? So if this queue here is not an array queue, then there's no way for the compiler to convert the guts of the other queue to an array, right? So that doesn't work. It'd be nice if it did, but the compiler can't magically do that. Yeah. So that's how you solve that problem. The equals is similar, right? You have to iterate over the other queue without changing the other queue, right? And so the only way to do that is to, because our queue interface doesn't have an iterator method. To iterate over the elements of the queue, you have to dequeue and then push it back in each time, right? Otherwise, you modify the queue that you're copying or the queue that you're comparing for equality, right? You always want to minimize the side effects that your methods or constructors have. If someone is asking you to copy a queue or test if it's equal to another queue, you don't want to change the other queue. Right? Yeah.
Since you'd have to compare all the elements,
Mm-hmm.
in order to get to like the elements in the middle, you'd have to like dequeue all the top ones.
Yeah.
So would you have to like store all of those in a separate like array or list or something like that?
No, so the trick is you dequeue the queue that you're copying or testing for equality with, and then you put it right back in at the end, after dequeuing it.
But if you put it right back in, then are you back at like the top? Oh.
No, it goes into the back, right?
Yes.
So it just goes around in a big circle. Yeah, so that's the trick. If you have a stack, it's harder.
Yeah, I was thinking about that.
Yeah, if you have a stack, right, now you need an auxiliary stack. So now you need a second stack because you can't, a second stack or a list or an array or a queue to store the elements in. Yeah. Yes?
Before when you were saying like set the back to like size -1 or whatever, why can't you just do like the this dot back equal to other dot back?
Because you don't know this dot back equals other dot back. When you're in this case here,
Yeah.
oh, because you don't know that the other queue has a back, right? You don't know how this other queue is implemented, right? Because it's the interface type here. It's not array queue here, right? So the other queue, it might be like a linked list-based queue, right? In which case, back isn't even an index anymore. It's a node, right? Yeah, so that doesn't work. All right, I think that's a good place to stop. What are we going to? I don't know what we're. I'm not sure what the next lecture is, but we'll do the. I guess we'll look at the next lecture in the next class. Anybody here not have their quiz 1 yet? I think. Hopefully, I have it here. Sorry?
I wrote the Friday section, but the Thursday lab.
Yeah. So. Oh wait, Friday, second, Thursday. Do I have those? Oh yeah. Wait, quiz 1. I probably don't have it. I have to ask. Yeah. So I have to get them back from Ben. All right. I guess if you wanted to, you could drop by the